and welcome to Dr. Pelupessy from Netherlands eScience Center. Thank you for your time in next two sessions. And the session from Dr. Pelupessy is about astrophysical multipurpose software environment. We have 90 minutes for the first session, and then we have a short break for 30 minutes after that, and second session from Dr. Pelupessy is from 2:30 to 4 p.m. Okay, Dr. Pelupessy, time is yours. Thank you.
Thank you for having me. Let me share my screen. I cannot share my screen at the moment. Is that correct?
Can you share your screen now?
Not yet. So I'm a normal attendee. Maybe that's the settings. Not yet. So I've uploaded so if somebody the presentation, if somebody else can share that, that would also work. So the actual error it gives is host disabled attendee screen sharing. Okay, yeah. So you should see my my screen now with the presentation. Please interrupt if you don't see it. Yeah, so thank you for having me. So I will give you an introduction to the astrophysical multipurpose software environment, or AMUSE, which is a package developed at Leiden University when I was a postdoc there, and has been developed from some years now. And I put some names that are in the current development team, but there are many others that have contributed. And of course, we need to thank them all for this. Let me first tell a little bit about myself. I was already introduced as being from the Netherlands eScience Center. You might not know the Netherlands eScience Center, but the Netherlands eScience Center is the National Center for Excellence for the development and application of research software. So we develop research software for scientists, and I mean, it might be interesting career path for you if you like developing research software. That this is something that's more and more being developed as a career path, because the research software engineering is recognized as a separate it's a separate skill, and more and more universities and institutes recognize this and set up either eScience research software groups or they hire them. So that's what the eScience Center is, but the eScience Center is also just a bunch of very nice people who like and share the passion for developing research software. And I myself have a background in astronomy, but the background of the people working at the eScience Center varies widely from computer science to chemistry, physics, and even humanities, because we span the whole range of sciences and support their work in the Netherlands. So today I'm going to host to you 2 sessions, and the first session is a lecture and a hands-on session. And my experience is that long lectures are kind of risky, in the sense that you can go on too long and you cannot absorb all the information. So what I think is more important for today for you is the hands-on tutorial that I've organized for you. So after about 30-45 minutes, I will stop lecturing, and you will be able to start the tutorial session. And in the second session will be almost completely filled with the tutorial and some exercises, and you can go as far as you want. The goals for today's lecture are I want you to sort of know what on a high level what Amuse is. I want you to gain some practical experience with Amuse, and ideally you would be able to have Amuse in your sort of toolbox for the future, if you want to calculate some simple numerical experiment in astronomy, and then that you turn to Amuse for that. And of course, maybe this will today might not be enough, but I've shared a link in the Slack of the school with the link to the Amuse Slack, where you can find more help and support when using Amuse, and of course also the repository and is also good for that. Okay, just not to keep this a secret. So the tutorials hands-on session will use the Google Colab, and you can start these are the instructions for starting the tutorial. Don't worry about this. I'll try to sort of walk you through it on a later stage. But if you're already itching to get going, then you might have a look. So the question we want to address is want to investigate the universe and the processes that happen in the universe. And on a large scale, the universe is dominated by gravity, and the gravity causes structure to form on the large scales. This is a drawing of the dark matter on very large scales from simulation. And if you look at the universe in more detail, then the structures start to emerge, and you start to see the other physics coming into play. And you can see this in this picture because of the quasar and the radio lobes extending from the center of a black hole in a big galaxy. And if you further zoom into single galaxies, you see that they're that they rotate under the influence of gravity, but they consist of stars and and gas. And the gas doesn't sit there idly. It clumps together and forms dense structures. And in these dense structures, new stars form. And the stars that form, they affect their environment by the radiation and the winds and the supernova that go off. And they shape their environment. So it's a quite complex environment. And of course, if you look in even more detail, you will see planetary systems forming. And eventually, if you want to know where our planetary system comes, we have to try to understand all the processes that happen. And one of the tools that has been developed in the last decades for this is the use of computer simulations. And of course, you all know that, but it's important to recognize the possibilities that the computer experimentation give you to bridge the enormous differences in timescales and to connect the different physical processes that interact and shape the evolution of the different systems. So what is AMUSE then? AMUSE then is a attempt to put the universe into a single framework. And the goal when developing AMUSE was to provide a simple environment to run and be able to use existing simulation codes, and to do so in a way that would enable new couplings between the different codes that are included in AMUSE, and in that way facilitate multi-physics and multi-scale simulations. Now that's a bit abstract, but I'll try to walk you through it in a little bit more detail. So this is just a sort of a bird's eye view of the key features of AMUSE. It's Python based and it interfaces different codes using remote function calls. And I'll go into more detail in each of the points mentioned here. So let me immediately show you what an AMUSE script looks like. So this is the sort of a minimal AMUSE script that contains all the ingredients that you will also find back in more extensive and more complicated scripts, because this script doesn't do much as a hello world script should, of course. The first thing to notice is that the scripts you write when using AMUSE are in Python. And this is standard Python, and of course nowadays that's not so amazing, but it was a good decision when we started AMUSE almost a decade ago to start using Python, and we found that it has been a very good choice. So what typically happens when writing a AMUSE script is that you need some pre-existing ingredients, and that you pull from the different parts of AMUSE with the imports. Then you want to set up a system, and that you do by generating initial conditions. You instantiate the codes that you want to use, and in this case that's only one, and that's a gravity code. You set the parameters, initialize the code with the model, and then you evolve the model what you want to do. What's not, of course, if you only use one code, there's no definition of the interaction between the different codes, but that would also be included if you use more than one code. And then at the end, you have done the run, and then you do your analysis and cleanup. So behind the scenes, there's a concept of different levels of interface to a code, and the user only sees the high-level interface. but there are low-level things behind it that drive all these things. And the idea behind Amuse is that you want to hide for the user the sort of the messy parts and the numerical implementation and the nitty-gritty and the details of handling the code and the data in the code. So when you actually run the script, then behind the scenes there are some things that happen that the framework maintains the code that you're running in a consistent state. But as I said, as a user, you will not notice this, that the framework is working hard for you. So another way to look at this is this is a schematic of the interface. The block that's marked code is your original code that can be in any language that has MPI bindings. So it can be Fortran, C, C++. We even have some Java codes, and that's wrapped by some layers of interface that are based on a remote code execution model. And the different codes that are managed by the framework run in parallel, and calls can be asynchronous. And Amuse provides a number of what we call interface services, the handling and the conversion of units, abstraction on the data structures in the model, the code state handling. So all these things are specified once in the development of the interface to a code, and once that is done, then the interface to a code becomes very uniform for different codes of the same type. So for different gravity codes, but also the codes of different types of physics. So gravity codes, hydrodynamic codes, they all are developed along the same or similar concept. So you would not be. It's not you can switch between different types of codes without feeling at a loss and without going through extensive manuals about and relearn a lot of things. So the idea really is that the user is presented with uniform high-level interfaces. So this is more or less what I just stated. So the tutorials will familiarize you with Amuse units, and basically we have a when we communicate with the codes, you never communicate with sort of naked numbers. You always specify a unit to a number. So a position will not be just a float, but it will be a float with a associated unit, and that is done with a units module. So the second tutorial will teach you about this, and you can basically it's based around the construction of what we call quantities, and it's a number with a unit, and you can handle quantities much the same way as you can handle numbers, with the exception, of course, that operations that are not unit where the units do not conform are triggering an error. So if you add a weight to a distance, then that's a nonsensical operation, and then it will give you an error. There are also constants defined, of course, where you can easily use physical constants, and there's an extensive list in the module. And you can, of course, do unit conversions. And the unit conversion part is important because it seems to be like a very easy operation to convert to units. But it is, in our experience, if you work with different codes that use different units and have different unit conventions, then yeah, a lot of errors stem just simply from the conversion errors, and that was what the little cartoon here alludes to, because you might remember that the NASA lost a orbiter around Mars due to a unit conversion error. So unit conversion errors are sort of, we try to prevent them by having the units module and by imposing the use of units. Then Amuse also uses a sort of an abstract data model for different codes. So if you there are two different base data models. One is a set of is a particle set, and the other is grids. And the difference is that particle sets are a collection of objects with different attributes that can, where the set is not fixed, it can grow and they can be combined. And grids are sort of immutable objects which are not all that different from a particle set, except that they're immutable and they can have different dimensions. They're implemented as there are different models for this. You don't need to know this, but they can be implemented as memory storage, disk storage, or they can refer to a state of a community code. And that's very important, that whatever the code uses internally for the representation of data, it's all wrapped in either a particle set or a grid. So you don't need to know about the internal workings of the code. You just need to know about the particle sets and the grids, and you can talk to any code in Amuse. Then the different codes. What's always annoying if you use a code is that you have some steps that you have to do before you can, for example, evolve a gravity code. And you have to do the steps in the right order. And of course, if you manage this by hand, then and you need to remember this, then this is a source of errors. And it's really not necessary, but because you can, what we do in Amuse is that we have a sort of a model of possible states of the code, and a model of the transitions that are allowed, and each transition corresponds to a certain function call. So if you want to do something, for example, you want to add a particle to a gravity code, then the code needs to be in a certain state. But you don't want to handle this state yourself. You just say, I want to add a particle to this gravity code, and then the framework figures out I need to be in this state, and I need to do these calls to get into this state, and I will add the particle for you, and then I'm in this new state. And if you want to do something else, then I will manage that. So you just talk to the code in very easy things. You want to add particles, remove particles, query the state of the particles, and then any internal state that the code might needs. For example, if you have a gravity code based on tree, on a Barnes Hut tree method, then it needs to reinitialize the internal tree structures. But all these things of connected to the internal numerical representation are invisible from the interface. So the framework will do that for you. So so what kind of codes are there in Amuse? We try to distribute the Amuse with a set of sort of useful codes, and we've made a sort of a rough distinction between 4 different types of code: the gravitational dynamics, stellar evolution, hydrodynamics, and radiative transfer. And there are a bunch of miscellaneous codes that can be, for example, be initial condition generators or codes that do some useful some other useful tasks. But these 4 physical domains, we try to have multiple codes in each domain that try to do the same thing, because it's important to have this, because this allows you to change codes very easily. Because all the interfaces to the codes are the same, it's usually a matter of changing one line in the script to change a code to a different, for example, to a different gravitational dynamics integrator, or a different stellar evolution code. And this allows you to do, well, it allows you 2 things. It allows you, for example, when you're developing the script, to use a code that's might be not so accurate, but very fast. And then when you have developed the script, you change back to a more accurate but slower code when you do your production runs. But it also allows you to validate and cross-check the results that you have between different codes. And really that's very important, because what you want to do when you do numerical astrophysics is you want to have reproducible results. And if you don't have reproducible results, or you need to do a lot of work, for example, to check the results with another code, then this will not happen. And then you are sort of in theory you can reproduce and check your results, but in practice it never happens if it's too difficult. So by having these homogeneous interfaces, this becomes a lot more easier. And really there have been a number of projects where this is just well, you basically people double check their results while they were developing their scripts instead of afterwards. So just let me quickly go to the different domains that are included. I think you've had lectures on this already, so there's no need for me to explain this. So of course, important physical process in the universe is gravity, and there are different gravity solvers included in AMUSE. And they vary in the approximations they take, the different time-stepping methods, the order of the integrator, whether they use smoothing, and then there are specials like post-Newtonian corrections, whether a given code might be assumed that the system is centrally dominated, so a planetary system. And then there are also codes that try to increase the numerical precision, etc. And as you could see here, the number of gravitational dynamics code is quite large, and well, you need to there are a number of codes that are often used, but there's so many different physical regimes in gravitational dynamics that you cannot cover them all with one code, and it's very important to have different codes available. So there's a tutorial on the gravitational dynamics interface, and that will basically try to familiarize you with the gravitational dynamics interface of codes. And basically this is all that you need to know to be able to use any of the codes that I just showed. Yeah, I don't need to explain this. This is more. This will be more concrete for you when you start using it yourself. Then the second group of codes concern stellar evolution. So solvers for the equations of stellar structure. I think you've had a lecture on MESA, and MESA is a modern stellar evolution code. So you should know all this. And MESA is part of a group of codes that are called Henry solvers. And so there are two of these in Amuse. It's EV-Twin and MESA. But in addition to this, there are a number of approximate stellar evolution codes that use more heuristic fit formula to try to calculate the stellar evolution. And of course, these are not so accurate because they don't solve anything in the internal structure for the stars, but they are as a result they are orders of magnitude faster, of course. So sometimes you're not so interested in internal structure and you can use a fast stellar evolution code. Other times you're very interested in the internal structure, but only, for example, if something happens to the star. So when you have if you have, for example, simulating a cluster, and then a stellar collision can happen, but that doesn't happen very often. So you don't need to, when that happens, you don't need to calculate the internal structure for all the stars in the cluster, but just for these two stars that have a collision, and then you calculate the internal structure, convert that to a 3D model, and then you calculate what happens in the collision. Things like that. So that's the reason why there are these different types of stellar evolution codes. When using the stellar evolution codes, actually they're very similar, whether you use a full solver or a fit code. Of course, the difference in the code, and I didn't mention this yet, I think, is that codes can have different sets of parameters. So it's always important to know what the parameters are that are available in the code. But from a point of view of use of the code, the thing that's shown here for SSE, one of the fitting formula codes, will also work with the MESA interface in Amuse. So the particles of the stellar evolution code will have attributes like age, mass, luminosity, radius, but also a attribute called stellar type, and that describes the evolutionary state in a sort of standard way. And then the evolution of a star can be described as a sort of a track through the different stages of the stellar types, and it can be a useful way to describe and think about how stellar evolution works. So the two additional domains included in Amuse, it's the gas dynamics and radiative transfer. And in the gas dynamics, there are two types of codes. They're like grid codes, and they discretize the space in regular fixed grids. And there are particle codes, and particle codes discretize the mass distribution in packets moving with the flow. And these so-called SPH codes, the smooth particle hydrodynamics codes, they have the advantage that they look a lot like gravitational dynamics codes. So, but these are the two types of codes that are available. I think for today the tutorial will not get you to the gas dynamics, but it's good to know that it's available. So let me skip this. So same thing with the radiative transfer. The radiative transfer, I mean, radiative transfer is a very complicated field. But what we've included now in Amuse is the most important process for affecting interstellar gas, and that's the the radiative transfer of UV photons and ionizing photons in the interstellar medium. And there are two codes for that included in AMUSE, Spray and Simplex. And they're also particle-based, so they integrate well with the gravitational dynamics and the SPH codes. And they calculate the transport of UV photons and solve for the ionization of hydrogen and helium and solve the thermal evolution of the gas. And well, they can be used anytime you have UV photons from massive stars or active collective nuclei affecting the interstellar medium gas, basically. So at the moment, the radiative transfer codes are mostly geared towards this process. And again, I'll skip this because it's not part of the tutorial for today. But the interface is very similar to the interface for SPH, and also very similar to the interface for gravitational codes. Okay, so that was a sort of a high intensity race to AMUSE, but let me slow down a little bit, because right now your brain is hurting with what AMUSE is and what you could or could not do. But let's step back and think about what does it do for you? Why would you use AMUSE and not a single code? So the first thing that the homogeneous interface does for you is it can simplify this. Just if you have a certain type of run that you want to run, it can simplify the setup and the run of the model. It's just a matter of writing a Python script. You don't need to go into the parameter files and setting up the directories, etc., etc. So that's already very useful. Then it also allows you to script simulations, because you're running from Python and you can do your evolve, but you can also do event detection, and when something happens in the simulation, you can detect that and change the simulation accordingly, or start up a completely different code, like in the example I gave for a stellar collision in a cluster. Then you can sort of take out the stellar collision and run it within the same script, run it with a different type of code. That process. Then you can also do what's called online data analysis. You can, while you're running your simulation, you have access to the state of the code to just in Python, and Python has a lot of tools for data analysis and so you can do that on the fly, and even in parallel with your run. Then it simplifies a lot doing ensemble simulations, because you can start up as many instances of a code as you want within your Python script, even if the code was not originally designed for that. And that simplifies parameter searches, optimizations, and things like data assimilation. And the other thing that is also, because all these codes have the same interface, it simplifies model comparison. You can run problems with different codes of using the same type of method, or you can switch methods. Maybe run a given hydrodynamics problem with a grid code and a SPH code. And the final thing that it allows you is it allows you to make coupling between different codes, and that allows you to construct completely new solvers. Okay, so there are different ways, different intensity of coupling, and yeah, and this is a whole like it's a whole lecture on itself. Is how you, what does it mean when you couple different codes, and when do you want to use different types of coupling, and when do you need when can you use amuse, and when it's not amuse, when it's not the best solution to use amuse. For example, if you have a very intrinsically coupled system, for example, a magnetohydrodynamics is a coupling between hydrodynamics and Maxwell equations. But you would never write a MHD solver in amuse, because the coupling between the Maxwell equations and the hydrodynamics is so tight that you would really need a dedicated solver for that. So in that case, you would include a magnetohydrodynamic solver within amuse. But there's a whole group, there are big classes of coupling where using amuse will make the coupling very easy and elegant to express and write. And an example of this, of a quite tight coupling, is the coupling between the gravitational dynamics of different systems. And for this, there's what's called a bridge included in amuse. So this is a way to couple different gravitational codes, and this is just based on the amuse interface, and that's enough to be able to use to couple the different codes. There's a tutorial on this, but yeah, I don't think for today we'll get there. Okay, so nice. We're nice on time. I wanted to mention. So at this point, I think the most productive way forward is if you try to get your hands dirty yourself. And the most practical way to do this, I mean, you can of course try to install if you have a laptop with Linux or with a Mac development environment. You can follow the instructions on the Amuse repository and the Amuse website and install it on your machine. But for this occasion, I think it's also it's enough to use the Colab, the Google Colab, because it works on there. So let me show you how it goes. Let me first check if anything on the chat. All right. So so if there are any questions at this point, you can ask them in the chat or in the Slack. I'll just show you how to get to the so if you go to the Google Colab, I think you have to have a Google account for this, but then you go to then you will land either here or you will land in a notebook where you can open a notebook. Then you search for Amuse code on the GitHub tab. Tutorial. Search, and then it shows you the different tutorials, and these are just in a repository, in this repository on GitHub. And then if you click on one, Then it will open it in a notebook environment. And then, well, the first tutorial is just an explanation of the notebook. So there's one important thing for the Google Colab is because the Google Colab doesn't have Amuse installed by default, of course, but you can run this by install this by running these what I call preamble cells. So if you go there and you do Shift Enter, you'll get a little warning that this notebook is not made by Google. Do you want to run it? I guess you want. And then it will start checking whether Amuse is already installed. And if not, it will install this. And this will take a little while, like depending on the Amuse components you need for the tutorial. It can be like a half minute to a few minutes. And then when it finishes, it will give you the output of this, and then with a few warnings, but don't be confused by that. It will work. So the alternative is to go to the website of Amuse, and there you have installation instructions if you want to install it on your own machine. Nowadays it's quite robust installation method, but of course if you have a different Linux distribution or different Mac system, then you can run into little problems, and then you might need some support to resolve that. But it's also an option if you want to have this on your own machine. So it finished here. So this is the output of the install. As you can see, it's a little bit messy, and it gives you warnings about packages not found, but it's okay. And so the second preamble that you need to execute is this one. These normally are at the top of the tutorial scripts. Okay, so that's the that's everything you need to get going, I think. So I already have uploaded the slides of the presentation. So there are some references in there, the instructions for the tutorial, and okay. So yeah, now it's your turn, I guess. So I'll be around checking the chat and the Slack chat. If you need any help with the tutorial or with the or any other, or you have any other question about Amuse. And then at the beginning of the second session, I will come back and maybe check on you and see what else needs. So the second section will be a completely hands-on session, except that maybe I will discuss some pitfalls and errors that are commonly encountered when starting with Amuse. But that will be more useful when you already have tried it out. All right, thank you.
I'm sorry to interrupt you. So would you mind to raise your hand? I just want to know whether any of you is currently trying the code, the Amuse, for example, or the Google Colab code. Okay, it's Shubham, Haru, Ferry, Shahna. All right, cool. Thank you. So I suppose it's about half of you who are currently trying the code. What about the rest? Do you have any difficulties, for example? Thank you for those who are raising your hand. And for those who are not, do you have any difficulties or questions or technical issues? Anything? Okay, thank you. Since none is responding, then I suppose you can go on. Yes. So initially I asked some of the participants, whether they're currently trying the hands-on or the tutorial or not. Hidayah, is there anything that we can help you with? Okay, I don't think so then. Thank you, and please go on with the tutorial.
Okay, everyone. Now we have a short break, and we'll meet again for 15 minutes after now to continue running many interesting script. Please try to running some of the script, and thank you for now for Dr. Pelupessy, and we'll meet again for 15 from now. Thank you.